All right, we're going to talk about radio astronomy, and in particular, we're going to talk about radio astronomy that's done by amateurs, not unlike us here. But I'm going to start out talking about a little bit of the history of radio astronomy and what it entails, and a little bit about what that's all about, and where it's going from here, and some of the interesting things that are going on with amateur radio astronomy. So we'll start out, and I mentioned that. I'm going to talk about what it is. I'm going to talk about the history a little bit. I'm going to talk about what the professionals are doing, what, the kind of things that we as amateurs can't afford to do, but occasionally get an opportunity to play with their stuff. But more talking about what we can do as amateurs, and then where you can find a lot more information about amateur radio astronomy. So first of all, I'm going to talk about the radio spectrum. So radio astronomy, as the name would imply, involves radio. And looking at this chart, you can see here's the visible light range. And this is what we're used to seeing. When we look in the sky, this is what we see as humans. Our eyes is visible light. But all of this spectrum down here, from basically practically DC all the way up to light, is considered the realm of radio astronomy. And these are all the frequencies that astronomers are looking at. Everything from below HF, looking at VLF, all the way up into the sub-millimeter waves. So, multiple thousand terahertz spectrum part there. So, and we do it from terrestrial, we do it from space. It's just a really an interesting field to study. So as I mentioned, that visible light is just a tiny slice. And this is typically, when you think of astronomy, you think of things like the Andromeda Galaxy, and this is what it would look like in unfortunately, we don't get to see that through our amateur telescopes, but if you were to look at that through a large telescope that had the light gathering power, this is what you would see is M31, the Andromeda Galaxy. But what's interesting is looking at the Milky Way. We can look at the Milky Way in infrared. So this is below what we can see as light, but it's above what you're looking at in radio astronomy. But this is a full sky or an all sky infrared image, covers our entire sky that we can see. And what that streak across the middle is the Milky Way. We can see some other artifacts here. This is a large Magellanic Cloud and the small Magellanic Cloud down here. So we see a lot of activity here in the Milky Way, infrared. So this is looking essentially at heat. But if we start looking at that same thing in radio spectrum, this is at 74 centimeters. So something we're familiar with, 70 centimeters, 400 megahertz. This is actually at 408 megahertz. And this is what the sky looks like. And the different colors denote different intensities of signal. And again, you can see those same things. There's the large Magellanic Cloud. There's the small Magellanic Cloud. Of course, the Milky Way galaxy looking out towards the core of the Milky Way galaxy right here. So that's what you'd see at 408 megahertz, if you could see it. Well, the next image, this is kind of where radio astronomy started. And I'll talk a lot more about this a little bit later, but this is a representation of the sky at two different frequencies. This one is at 160 megahertz here, or megacycles actually. And this one's at 400, I think it's 460 or 480 megacycles. These are like isobars. It's a contour map of the sky, essentially, that's showing the different signal intensities. And this leads us to where we do what we're doing today. So I'll talk a little bit more about this and where this came from. But this all started back in the 30s. A fellow by the name of Carl Jansky was an engineer at Bell Labs. And he was, if you think about Bell system, in the early 30s, they were doing transatlantic telephone circuits on HF. And one of the problems they were dealing with was noise. So he was tasked with figuring out where this noise is coming from. So they built a large steerable array. He's tuning around 20 megahertz, which is an interesting frequency. I'll talk about that a little later too. But he found three interesting sources of this noise he could pinpoint. There were nearby thunderstorms, okay? There were distant thunderstorms, of course, but there was this pervasive hiss in certain directions. And that pervasive hiss seemed to stay in the same locale in the sky. Now, it doesn't mean that it's a fixed point in the sky. It's a fixed point in the stellar sky. Okay, so you like looking at a star, that star moves. it's moving with the stars, whatever he's listening to, whatever he's picking up. This is his antenna. I love this. I'd love to have that in my backyard. Wait a minute. I almost do. I'd love to have that in the backyard. That's just a beautiful array. It is just a wonderful looking thing. Well, the hiss was interesting. You know, there was some interest in it. He figured out, well, it isn't the sun. It's not the sun. And it was located in this fixed position in the sky that, you know, that moved with the sky. His conclusion was that it was the core of the Milky Way galaxy. And with that, they stopped pursuing it. They didn't look into it any farther. But technically, we look at Carl Jansky as the founder of the discoverer of radio astronomy. He is the guy that really first discovered that there's radio waves coming from someplace in outer space. And we honor him today with the unit of signal strength in radio astronomy. It's called the Jansky. Now, there's an amateur radio connection to all of this, which is really fascinating. This fellow, Reber. Reber was W9GFZ. He was an amateur radio operator. And he was interested in investigating some of this stuff. So he builds a 9-meter dish in his backyard. Oh, yeah, I like this guy right from the start. 9-meter dish in his backyard. He started mapping the sky at 160 megacycles. Okay. It took him 3 tries to get it right, though, because he was dealing with all kinds of problems. He started at higher frequencies, moving down. He was dealing with limited hours of operating because of interference that he was getting. Primarily, one of the things they talked about was interference from taxi radios, which I got a big kick out of. But ultimately, he published a paper called Cosmic Static. It was published in the Astrophysical Journal in 1944. And this actually marks the beginning of what we call intentional radio astronomy. It's deliberately looking for things in the sky. This is the beginning of radio astronomy. So this is Grote, quite a guy. There's his dish in his backyard, the black and white. The photo on the left is the dish that has been relocated and set up as a display at the National Radio Astronomical Observatory out in West Virginia at Green Bank. So that's pretty cool. You can actually go and see that. But that's his setup. This is what his data looked like. So he's using a strip chart recorder and he's recording signal strength, right? That's what all of this is. And ultimately, he's able to take those readings and create those charts that I showed you earlier. So those are his contour maps of the sky based on those recordings. So this is where it all started. Well, there's some other interesting things that come out of this. One, first off, is he's dismissed. Everybody's doing optical astronomy. The contemporaries say, no, radio isn't interesting. Optical is the way to go. We've got to do optical astronomy. It wasn't considered important research. Boy, little did they know. But he did persevere. Thankfully, he stuck with it. He remained an amateur radio astronomer until his death, which is incredible. He worked with NASA, doing certain types of research at VLF and medium frequencies. He relocated to Tasmania, and he liked Tasmania because it had good transparency in the ionosphere, as he put it. And they worked experiments with NASA and the space shuttle at medium frequencies and low frequencies, VLF. And so this is one of his later contour maps, and this is at 144 meters, or a little over 2 megahertz. So he was doing this well into his aging years, and I just really admire that and really respect what he did. He gave us a lot, but he did start something. What came out of this is, you know, one of the things out of optical astronomy is you use spectroscopy to look at the visible light to identify elements and compounds located in stars, in their light. You can identify the spectrum of that star. You can identify the elements. You can identify the compounds and what have you. Well, it was predicted that we could do something with radio. There's got to be some radio spectral lines as well. And so a fellow by the name of Jan Oort in 1944 describes it. He predicts that this is possible. You may recognize that name, Jan Oort. If you've ever heard of the Oort cloud, that's who it's named after, which is the cloud of cosmic debris out beyond Pluto's orbit. Anyway, one of his students, Hendrik van der Holst, was tasked with figuring out what the spectrum is, what it is, and how to identify it and how to detect it. Well, they decided to look for the spectral line for hydrogen because it's the most abundant element in the universe. So why not look for that one? It ought to be the easiest one to find. It should be trivial. And they predicted that it would show up at 1420 megacycles. Well, it wasn't so easy to find it. It turns out that what causes this emission is a transition from ground state in a hydrogen atom, and it occurs very rarely being 2.9 times 10 to the minus 15 times per second. That's not very much. But one way to look at it is hydrogen is the most abundant element in the universe. The universe is pretty darn big. And it's estimated that there's probably on average one hydrogen atom per cubic centimeter in the universe. So it's a lot more common than you might think for these things to take place. Well, a few years later, in 1951, Evan and Purcell, a grad student and his professor at Harvard University, actually detected the hydrogen line. And I love this telescope. This is a guy after my heart. You know, if you like vintage gear, that is just wonderful. That's like something I might cobble together in the garage, you know, but I see a lot of familiar looking stuff there. There's some waveguides he used. It was a simple system. It was this horn antenna, and it's what's called a drift field telescope. So it uses the Earth's rotation to scan the sky at a given elevation. Okay. So it just has a simple diode detector, and he's measuring a simple diode detector, and he's tuned to the frequency that they're looking at, 1402. And lo and behold, they found it. Well, this earned them, of course, a Nobel Prize, but there's a lot of significance. They did detect the hydrogen line at 1420, and it's some spare change. So it's 1420.404, some 575, something like that. I can never remember it. But they detected some other important things like Doppler shift. With the Doppler shift, looking at the Milky Way, they were able to measure directly the angular velocity of the Milky Way. In other words, how fast is the Milky Way turning? They were able to do that. It also revealed the spiral structure of the Milky Way. Now, if you're familiar with the research that was going on prior to this, we had folks like Edwin Hubble, who was really the guy that figured out that we're in a galaxy, because he was looking, you know, they were looking at what they thought were nebula, but Hubble figured out that these are galaxies, all these little splotches of light in the sky. They are besides nebula, they are other galaxies, and we are in one of these galaxies. But they had no idea what the galaxy looked like. With the hydrogen line, they were able to figure out what our galaxy actually looks like, and reveals that spiral structure. And this actually forms the basis of modern radio astronomy. This is key to what's going on today. Hydrogen line measurements are continuing to this day. They're constant. It provides a view, of course, of the local galaxy as well as distant galaxies in our universe. So it's pretty important stuff. So one of the things that comes out of this, though, and we'll talk about this in a minute, and I'm sure you've heard of it, it will lead to a conundrum, but we're going to talk more about that later. Oh, I guess I really don't need to show this next slide, but I'll just mention it. Hydrogen line ends up what we call the water hole. This is actually a protected chunk of spectrum. ITU protects this chunk of spectrum for roughly 1400 to 1600 megahertz. And this is where hydrogen line exists. And the atmosphere is fairly transparent, that water hole. It doesn't absorb a lot of that energy, so we're able to view that quite easily. So that's if you ever hear the term the water hole, that's what they're talking about. So radio spectra of elements and compounds. Each element and compound has a unique wavelength, its spectrum. These are emission and absorption spectral lines. So emission meaning that it's actually emitting that frequency, or absorption meaning that it's in front of something, that we're actually absorbing something in front of the source is absorbing that frequency. And so that's how we can detect it. So there's a source of energy behind, let's say, like a cloud of dust. We can determine what's in the dust by those absorption lines. So these are the emission and spectral emission and absorption spectral lines. So hydrogen, I mentioned, is 1420.40575. That is the hydrogen line. But one of the next ones that was discovered a few years later was hydroxyl, our hydroxyl ion, OH. That's right around 1660 megahertz. Another interesting one that's quite abundant and easily detected is carbon monoxide. But look at the frequency that that's at. Look at its spectral line, 115 gigahertz, 2.7 millimeters in wavelength. That takes some pretty sophisticated equipment to do that. There's lots of elements and compounds in the universe. So far as the time I did this presentation, it's been a few years. I haven't checked to see if this has changed. It may have changed in recent years. But so far, with radio astronomy, we've detected 70 molecules and many compounds in the universe, 70 molecules and compounds. In total, some 225 compounds have been detected. Some of those are complex organic compounds, which is kind of interesting because that's the key to life, those complex organic compounds. So, this is one of the interesting things that comes out of radio astronomy is detecting these things. So radio astronomy had evolved. We talked about the guys at Harvard. We're going to talk about John Krause. Some of you may have heard of John Krause. He's a rather famous amateur. He was a professor at Ohio State University. Published the definitive book on antennas, many revisions to that. I happen to have a couple of copies of that in my library. It's a wonderful book that he wrote. But he began this work in the 40s at Ohio State. He built something in the 50s called the Big Ear. You may have heard of this, the Big Ear. It was constructed at a cost of $250,000. I need to figure out what that is in today's dollars. It's probably in the tens of millions, I'm sure. But at the time, it was the largest radio telescope. It was the size of a football field. It was big. But it's not what you think. It's what's called, again, that drift field design. So it uses the Earth's rotation for what's called right ascension to move through the sky. And you set the declination or the elevation of the antenna and allow the Earth's rotation to scan the sky. So this is the idea, and the declination is changed by tilting a flat reflector. Now, what am I talking about? Here's the telescope. Now imagine this football field sized thing here. There's the tilting reflector. This is a partial parabolic reflector. So this is a segment of a parabola. So he's going to get some gain from this, and then he's got some big feed horns. That's the receiving end right there, are the receive feed horns. We take some closer looks at these things. These are some photographs of the parabola, the fixed reflector, the tilting reflector, and the feed horns right here. And there's another view of those feed horns. That's quite a piece of equipment. One of the interesting things that came out of the Big Ear, if you've ever heard of the WOW signal, anyone who follows SETI, its Search for Extraterrestrial Intelligence, has probably heard of the WOW signal. This is where it was detected. It's never been explained. It's never been duplicated. It was something of extraterrestrial origin. It was not a glitch in the data. There was actually, they believe, something there, just no idea what it was. But interesting thing. But that led to the creation and the formation of SETI, believe it or not. So that started with these guys here, John Krause. So another major discovery popped up shortly after that in the 60s. Penzias and Wilson at Bell Labs. Here we are at Bell Labs again. One of the things they noticed that everywhere they pointed their antennas, there was this constant microwave noise. Now, what they were working with, if you think back to the late 50s, there was a thing called Project Echo, Echo 1. Echo 1 was a passive communications satellite. It was just a reflector. And it was in low Earth orbit, and it was tracked by a big antenna that followed the thing through the sky, and they could reflect signals off of it. Well, that's what these guys are using in their experiments. And they're trying to figure out where this noise is coming, because it's background noise. It's not noise in their system. It's coming from the sky. They have no idea what it is. One of the funny things was that this antenna had sat dormant for a number of years. The Echo 1 was that was done in 1959 is when they ran that. And then Telstar, it was used with Telstar, if you remember the Telstar satellites, in the early 60s. But the antenna was filthy with bird droppings, and they figured, well, the bird droppings are causing the noise. Well, that didn't make any difference whatsoever. So I love that. But this constant microwave in all directions, and it's invariant. We know today it's invariant within 0.01%. So no matter where you look in the sky has that same noise level. Temperature, as we would call it. It's a temperature degrees Kelvin. Well, Dickey at Princeton figured out what it was. And today we know it as the cosmic background radiation. It's the remnants of the Big Bang. Remnants of the Big Bang. And it's the background noise of the universe. It's pervasive everywhere we look. It's 5 degrees Kelvin. That's the background temperature of the universe. It's one of the longest running data collections going. We're still running this, and basically they end up refining the data even more accurately than that 0.01%, which is pretty amazing to me. Lots of observatories are involved in this. They do both ground and space-based observations. The interesting thing is, of course, this is all supporting the Big Bang theory. Remember, it's just a theory that was proposed by George Gamow a decade earlier. So this actually showed, this was some evidence that what George Gamow had proposed was possibly reality. So that's interesting. Again, radio astronomy comes to the rescue, figuring this stuff out. So that was a big discovery. This is a photo of that horn. Not what we think is a microwave dish today or a satellite antenna or something, but that's what was used for Echo 1. And I remember seeing these things as a kid and just marveled at that. I'd say, I want one of those in my backyard. So let's talk a little bit about some of the technology. The earliest radio telescopes used a single antenna. And they, out of necessity, they had to be bigger to be better. Bigger is always better, right? Need more light gathering power, as we call it. So bigger telescopes. So these physically huge single dishes, like Jodrell Bank, England. Green Bank, West Virginia was another big one. And I say was for Green Bank because it's been replaced by one that's even bigger and better. But one of the ones that was, of course, was Arecibo. And we're all very sad about that. And it's actually heartbroken. That was such an incredible instrument to lose. Just an amazing piece of technology. But we don't need big telescopes anymore. We don't need big antennas. We use what's called interferometry. We use multiple antennas separated geographically with multiple receivers. And the greater the geographic separation, the more resolution we can attain by that telescope. And we synthesize essentially a planet-sized antenna. That's what we can do. But it does require precision timekeeping. So things like, I know I'll talk about this one system. They use their timekeeping is done by using a hydrogen maser as their frequency standard to set their time to be able to correlate their data. So it's pretty interesting stuff. The correlator, you can either look at a single frequency or a continuum. In other words, a big chunk of spectrum. They look either way. That's when we talk about continuum or single frequency. So an interferometer, simplest explanation, there you see it here. You've got some stellar source, you've got radio waves impinging upon two dishes that are separated. So the signal arrives at different times here, but you adjust that with a phase shift. So they arrive at the same time so that you can correlate them and generate an output. Now, this is the earliest type of interferometer. It's interesting that as the technology progressed, the phase shift could be done by switching in different lengths of coaxial cable. So that the antennas are maybe a few thousand feet apart, and you've got a couple of thousand feet of coax feeding them. And your phase shift is done by changing the length of the coax, by switching in different lengths of coax. The next step from that was to go optical, and they use fiber optics and switch in fiber optic different lengths to change that phase shift. The current technology, it's all done in software. It's amazing what they're doing now. So it's all done here. None of this is is here. It's all combined in software. The correlation is all done in software. The phase shifts are all done in software. So if you know where the antennas are, they can be anywhere, and you don't have to have the all these multiple feed lines. You'll see VLBA, very long baseline interferometer, is multiple thousands of miles wide. So currently, our National Science Foundation runs a number of observatories, and the biggest, of course, is the National Radio Astronomy. I always want to call it the National Radio Astronomy Observatory. I always want to call it the National Radio Astronomical Observatory. It's the National Radio Astronomy Observatory. They run a number of telescopes. One, which you're probably familiar with, is the VLA in New Mexico that's operated out of Socorro. That's where their instrumentation is. But the VLA out in New Mexico. I mentioned the VLBA. This is the Very Long Baseline Array, and there are antennas in Hawaii, Virgin Islands, Washington State, Maine. They're all over the place. There's about 10 antennas involved in that. Also in Green Bank, West Virginia, is the Green Bank Telescope, which the Robert C. Byrd GBT, which is that's the largest movable structure in the world, which is pretty incredible. It's huge. It's also a size of a football field. That dish is usable to 300 gigahertz. So it's being used in basically sub-millimeter wavelengths, and it's the size of a football field. So that's some piece of technology. We also have, I mentioned Arecibo, the National Astronomical and Ionosphere Center in Puerto Rico. So that dish, of course, is gone, but there's still an observatory there. They still are active. There's still a lot of radio telescopes there. They're still actively pursuing research. So NAIC is still part of NSF, which is good to know. I don't know if they'll ever rebuild Arecibo, the big dish, but who knows? That was the largest, at the time, was the largest ever built. Now China's got the biggest dish that's a mile across. That's just staggering to me. That's immense. So there's the VLA. Some of you may have visited the VLA. I mean, they do encourage visits. They have a visitor center. You can tour the facility there. The VLBA, I mentioned 10 sites: Hawaii to Virgin Islands, Washington to New Hampshire. I said Maine, it's New Hampshire. Apologize. They cover a non-contiguous bands within the spectrum from 300 megahertz all the way up to 90 gigahertz. And it operates out of Socorro. That's where their headquarters are. Now, this is the thing that when we start talking about resolving power, we're used to resolving power of optical telescopes. We're used to thinking about the resolving power of something like the Hubble Space Telescope, or now the James Webb Space Telescope. Get this. If this thing was able to resolve visible light, you could read a newspaper in Los Angeles while standing in New York. That's the resolving power of the VLBA. That's pretty amazing. That's one of the antennas. That's the one just right up the road from us a little ways in the Owens Valley at the Owens Valley Radio Observatory. But this is on their property, which is Caltech, but it's operated by the National Science Foundation, NRAO. I mentioned the GBT. There's the GBT. Interesting. If you think about this is an interesting aspect of this. If I look at something like this, it's quiet. This antenna, this is a single dish antenna. This is the feed. This is a Cassegrain feed. This is where the feed horns are down here. This is a subreflector, and there's the feed horns. One of the things you note about this is you've got this structure, and the structure causes interference with the incoming waves. So it does degrade the signal because of all this structure. If we look at GBT, this has a rather unique design for a radio telescope. Take a look. If you've got DirecTV or Dish, any kind of satellite television, DBS system, it's called an offset fed. Here's the feed up here. It's actually outside of the optical path of the telescope, the main reflector. So you don't have that obstruction in the field of view, which is marvelous. You don't get those interference patterns in the signal coming in. You don't have to remove that stuff. You don't have to work with that. It's free and clear. So this is the main reflector. This is about 100 yards across, roughly 300 feet. There's a subreflector up here, and this is where the receivers and feed horns are, right there in this structure. This is actually considered, it's an active surface. They use lasers to actually move the surface of the dish to correct it. That's how they can get this thing to operate up at 300 gigahertz, because they can actually manipulate the dish to make it optically correct. So what kind of stuff can you see with this? Well, I'm going to give you one example, because this is kind of an interesting image. I love this image. Every time I look at this, it just blows my mind. This was something what was called the Canadian Galactic Plane Survey. And this is a composite image of Cygnus, the Cygnus region of the sky, if you're familiar with where Cygnus is, within the Milky Way, pretty much overhead when the Milky Way is overhead at that time of year and time of day. This is looking at multiple spectrum. These are continuum as well as specific frequencies, but we're looking at 74 centimeters. Those are the reddish colors that you see in here. That's at 74 centimeters, 21 centimeters. They're looking at hydrogen. That's the green stuff in here. That's hydrogen. They're looking at the 60 micron, which is infrared. 60 micron is the turquoise color, and the blue down in here is 25 micron. So this is an amazing image of a huge swath of spectrum looking at Cygnus. And we can see things like nebula. These are all basically a supernova shell. That's what this guy is down here, is a supernova shell, and that's probably what this is up here. Just really incredible, the kind of things you can see with a radio telescope. You could never see that with an optical telescope. It's not there. We can't see it. So that's some of the cool stuff that they do. Well, let's start shifting gears a little bit, and let's talk about what we can do. You know, those guys, the pros, they have all those cool big toys. Well, we can't do that. You know, we really can't afford to build a 300-foot dish in our backyard. We can't afford to build a 9-meter dish in our backyard. But what kind of stuff can we do? And this is really fascinating, because you're going to be surprised at the stuff that you can do with what you have in your ham shack. I kid you not. You can do this. There's several areas that amateurs do to observing. First of all, VLF, very low frequencies, solar observations. So what are we looking for in solar observations? Well, we're going to show you like some examples of that, but primarily VLF is solar. We're going to talk about HF observations, and these are planetary observations. So things within our solar system that you can look at with HF. And amazingly enough, you probably have the equipment to do it. It's stunning. But then we'll talk about microwave, and this is where we start getting into the hydrogen line, talking about hydrogen line and all of this, as well as radiometry. Radiometry is a real easy thing to be able to do with microwaves. So there's lots of opportunities for amateur astronomers to play with this stuff. And it can, in terms of outlay of costs, what it comes out of your pocketbook, it can range anything from free to tens of thousands of dollars. So when I talk about free, you're going to be amazed by free, because if you got a computer and a web browser, you can play with a radio telescope, which I think is astounding. But if you got an old DirecTV or Dish network antenna, you can build yourself a real simple little radio telescope, and it won't cost you an arm and a leg to do it. So let's talk about VLF, the solar observations. Well, we all know that solar activity disrupts HF communications. You know, solar flares, coronal mass ejections, CMEs, these all disrupt this stuff. Well, VLF is also affected by those disruptions. More importantly, VLF has been used for years for distribution of time. The so-called, your wall clock, that's a so-called atomic clock, synchronizes to WWVB in Fort Collins, Colorado, that's running down at 60 kilohertz. Well, it relies on ground wave and sky wave at those frequencies. And if we should happen to have a CME, a coronal mass ejection, it disrupts those signals. You know, those signals are pretty much there all the time. It 24 hours a day, it transitions from the ground wave to the sky wave, what's called the diurnal cycle. But if there's a CME, a large solar flare, it disrupts that, and it's easily detected with a VLF receiver. It's a simple instrument. If you want to put one together, it won't cost you a lot of money. You may even have the stuff to do it, which is kind of cool. It consists of a WWVB receiver and what's called a comparator. and a stable reference clock nearby. And what's happening here, what's interesting is amateur astronomers using this equipment have been exploring gamma ray bursters and their effect on VLF propagation. This is a new field. Amateurs are actually playing with this, gamma ray bursters. Gamma ray bursters are something that is very active in astronomy, both optical astronomy as well as radio astronomy and beyond. Looking at this, trying to compare what causes a gamma ray burster, and they're being detected by seeing interference with VLF, which is kind of cool. The other thing is amateurs have discovered meteor showers that were unknown to exist prior to the time by looking at how they affect VLF propagation. Interesting. The other one that you might be familiar with, sudden ionospheric disturbances, SIDS, and earthquakes. There's research being done at VLF, and this is the kind of stuff you can do. You can do this as an amateur, which is amazing to me. Citizen science. So what does it take? Here's a typical setup. This is a HP 117A VLF comparator. Typically, you can pick one of these things up for $100 on eBay. Might even have somebody give you one. I've had several of them given to me, so they're really easy to come by. And you just need a stable reference. And in this case, I used what was originally used with these things is just a stable crystal oscillator. And this, what you get is a phase comparison between the signal, a phase locked signal to WWVB and the crystal oscillator. And you measure the phase difference between them. And you record that on a strip chart right here. So that's about as basic as it gets. Something a little bit more sophisticated is a spectrocom. I have one of these guys as well. They're a little bit more expensive, but the HP works just fine. And what sort of things am I going to see? This is a typical strip chart from the spectrocom. And you see this nice, beautiful, clean phase. This is what it should look like right here. This is the phase difference between the signal I'm receiving from WWV and my local reference. But all of a sudden, I get all this stuff. This is typically what a coronal mass ejection, a CME. This is caused by a CME. You'll see this lasts for a couple of hours, and it takes it some time to recover from it. So this was some kind of a small event that took place. But this is the kind of stuff that could be detected with this equipment. This is the stuff that leads to what we know about space weather and propagation. This is key to that. So that's VLF observations of sun. Let's talk about HF. There's an interesting project going on right now called Radio Jove. Jove, Jovian planet, Jupiter. That's Jove. This was started by NASA and the University of Florida. And the whole purpose of this was to observe volcanism on Jupiter's moon, Io. That's what it's all about. But it turns out there's other things you can discover with this. So they're looking at the volcanism. Now, these are sulfur volcanoes on the surface of Io, and they emit radio waves at 18 megahertz. That should be pretty easy for us to hear. You know, if we're in a quiet location, we got a general coverage receiver, 18 megahertz is a piece of cake. But there's more. 20 megahertz. There's electromagnetic emissions from Jupiter that are quite detectable on Earth, and they're also predictable because they're both the volcanoes, the 18 megahertz sulfur volcanoes, as well as the EM storms, are predictable because of the positions of the moons around Jupiter. So if you know where the moons are, you can actually derive where you'll be able to hear, when you'll be able to hear these things. And all it takes is a quiet location and a small Yagi antenna and a decent receiver. And if you want to see the predictions, you go look at spaceweather.com. It's a great website, and they talk about this on spaceweather.com. So if you've got yourself a nice, good low noise receiver, you know, a decent HF receiver, general coverage, and most modern receivers will cover those frequencies, and a decent antenna, you know, small Yagi for that frequency, you can actually detect this stuff, which is pretty neat. So spaceweather.com. But you can get more elaborate, you know, with HF. We could probably, I'd like to see somebody build an HF interferometer as an amateur. This is already being done by the professionals. In fact, Right up the road, 100 miles at Owens Valley, they've got something they call the LWA. That's the long wave array. And that covers, I think, 14 megs to roughly 100 megahertz. That's their array. And they've got something like 128 antennas in it's large interferometer. So it's a neat system. But HF interferometry, a couple of antennas, a couple of receivers, I could see doing that. That would be pretty neat. And some means to correlate the data that you receive. So let me talk about Radio Jove in a little bit more detail. The whole purpose of this is it's a STEM program, science, technology, engineering, and math, trying to get kids involved in science and mathematics, and in particular radio astronomy. Radio Jove provides inexpensive resources to anyone who's interested in pursuing this, and they have lots and lots and lots of background material online. You can purchase as a kit the entire telescope, save one part. You get the kit. The whole kit is $225. It consists of a receiver and an antenna, but you have to add supports for the antenna. It's basically a dual dipole. You have to add the supports for the antenna. The software is free. You can download it. You can download the software anytime. It's something called Radio SkyPipe. And the other piece of software is called Radio Jupiter Pro. And these are designed to work with the Jove kit and detect these signals from Jupiter. So if you're involved with kids in high school science programs, this might be an interesting project to get them involved in. It's low cost. It's not going to break the bank. It's really kind of an amazing thing. And like I say, there's a lot of information on this online. So one of the observatories, this is located, I believe, up in Canada, the Starlight Cascade Observatory, and they built one of these systems. And there's their receiver, there's their antenna. You can see the 4 supports, and there's basically 2 dipoles. You can see a feed line there and a feed line there. And this is listening at 20 megahertz. Now, what kind of stuff have they seen? One of the things that they published that I thought was really cool, this is at 20 megahertz. There is an X-class solar flare. That's what it does. That's the sort of thing that it does at 20 megahertz. So not only are they getting science from Jupiter and its moons, but they're also doing solar astronomy with this. They're actually detecting an X-class solar flare, which is pretty interesting. That was in 2014. I do remember that one when it occurred. That was a pretty major solar flare. That was very disruptive. It was a big one. So, and interesting stuff. And this is all done, done with the computer software. Again, the software is free. The kit itself is very inexpensive. So if you're involved with kids in science programs, there's a great project right there. So let's talk about microwave radio astronomy. Now, one of the easiest things to get into, I mentioned radiometry. Radiometry is a process of just measuring total power, essentially, is what you're doing. So total radiated power, whatever you want to call it. And typically we're going to do that with the sun, but there's lots of other things. If you build a sensitive enough telescope, you can do this with a lot of things, but in particular, the sun is an easy target. We measure the total power generated by the sun within a given radio bandwidth. And it's a simple system. You might even have the stuff to do this one. If you've ever played with satellite television systems or satellite dishes, you've probably got everybody's got a spare dish lying around, right? DirecTV or a dish network, the LNB, the low noise block down converter, these operate in the KU band, and you need a power source to be able to power that block down converter. And what you're going to use for a receiver and what the means to detect and collect is one of the tools. It's a little device that they use for aligning satellite dishes. It's basically just a detector and a meter. Real simple. There's nothing to them. Lots of companies make them. They're powered by a battery, and all you need to do is hook one of those up to the output of the LNB, power the meter, and you've got a radiometer. So this telescope, again, uses what I refer to as the drift field technique, where the antenna is at a fixed point in the sky and the objects you're looking at just drift past it. So the simplest one to do, and I love this guy, Peter Wong, built this thing, and there's you can go to his website and check this thing out. It's the itty bitty radio telescope made with an old satellite TV dish. I said DirecTV, it's not really a DirecTV dish. It's actually just a sat dish, but itty bitty radio telescope. So he's got the low noise block down converter right here. He's connected up to this. This is the device I'm talking about called a sat finder. That's what you use to align. These have been used for years. If you had one of the big old C-band TVRO systems, you used a sat finder to align that dish. That's what, and you use them now to align the DirecTV and the dish network dishes. That's what they get used for. And of course, you've got a little 9-volt battery down there to power this. So this is about as simple as a telescope gets, but it's amazing what you can detect with this. This will actually detect not just the sun, but you'll find that the ground generates energy, and you can detect it with this. If you do any kind of microwave radio, if you're involved in 10 gigahertz, you'll find that this is a pretty simple thing to do with your existing radio. If you point the radio at this, we use the sun as a noise source for testing radios in microwave. But you can also look at the sky noise versus the ground noise. You'll see a difference in level, just looking at open sky versus looking at the ground. The ground is radiating heat. It's thermal energy that happens to be in that frequency range, and it does detect it. So it's an interesting use of the technology, and it's very simple to build one of these. But let's talk about something a little more complicated. Let's talk about hydrogen line. How do we do that? What are we going to do? We're going to look at the range of 1400 to 1600 megahertz. Now, I said you could do this for free, and this is one of the things that this just blows my mind. There's a fellow over in Italy who's created something called Pictor. It's an online, web-based hydrogen line telescope, and it's free to anyone who wants to use it. You can connect up to it and do observations, and I've done this many times. It's really a neat tool. But one of the things that he encourages, you can build your own. It's a real simple system. It just consists of a small dish, a low noise amplifier, and basically a down converter or one of the little RTL dongle SDRs is what he's using in his telescope. It's real simple to build. He's got all the information on his website. It's all open source, so the software is freely available. It doesn't require a lot of elaborate equipment. Again, this is a drift field telescope, so you point the telescope at a single point in the sky and allow the Earth's rotation to allow the sky to travel past the telescope, so you get a swath of sky, and you can change that elevation, and within a certain amount of time, if you've got the time to do it, you could actually get an all sky picture at hydrogen line, which is interesting. Bigger is better. You could use an old TVRO. I don't know if you've ever heard the term, we call them buds, big ugly dishes. You can find one of those things for free. Somebody may even pay you to take it away if they want to get rid of it. But TVRO dishes, this is like a 3-meter satellite television dish that we had decades ago. They've been replaced by the things like DirecTV on KU band, but big ugly dish. You need that low noise preamp and a down converter. And I mentioned the SDR, like an RTL dongle, and the software. This is the software, RF Space or Cloud SDR, SpectraView. All this stuff is available freely to play with. My alarm's going off. So we're not a huge expenditure. This is something that you could actually build yourself, and we've actually done this. We've actually built these and played with them. It's kind of a cool thing to mess with this. It's a pretty simple thing to do. And again, like I say, many of you may have the equipment to do that. All of this is available on GitHub, if you're familiar with GitHub. Open source. That's all open source material. So that's where you can find all this. Okay, if you got deep pockets, you can buy a radio telescope. There are companies out there that make these things commercially available, and I'll give you some examples of those. But you don't need to build anything. You just need to assemble it. You buy it and put it together. You don't have to build anything from scratch. It's a telescope ready to go. So you see the extremes, from free online web-based radio telescope to spending tens of thousands of dollars to build your own interferometer. So it's, for amateurs, it's just like amateur radio, everything from QRP to the megalithic contest stations that we see. So it's an open world out there for whatever you want to get involved in. But I like it. Just buy a telescope. So what are you going to do with this? If we go build this microwave radio telescope, what am I going to look at? Well, I'm going to look at the Milky Way, just like our friends in the past have done, Grote and Reber and Evan and Purcell and all those guys, all the stuff that they looked at. They were looking at the Milky Way, and that's easy to look at. In fact, you can do that with the online telescope, and I'll tell you a little bit more about that in a minute. Cassiopeia A is the brightest radio source in the sky, except for the sun. The sun really is the brightest radio source, but Cass A is actually very bright, and a hydrogen light telescope will easily pick this up. It's a supernova remnant. And another interesting one is Cygnus A, Sig A. This is a what they call a radio galaxy. It's the second most energetic radio source known, and it's another galaxy some distance away. And it's easily detected with a hydrogen line telescope. Actually, Sig A has been observed from low microwaves all the way up through X-rays. So this is a very, very common observed. The professionals are spending a lot of time looking at this, but amateurs can look at this too, and you'll see the same stuff they see in many ways. Taurus A, Tau A. It's the Crab Nebula, M1, another supernova remnant. Very noisy little guy. And of course, Virgo A is another noisy source. And I mentioned Sol. Sol is by far the noisiest object in the sky, but you can't see it at night. You don't hear it at night, but these other guys you can hear anytime they're in the sky. That's what's neat about radio astronomy. It doesn't have to be dark. You can do it in daylight. It's not dealing with visible light. We're dealing with radio waves. So let's see a little bit more about this. One of the things that you can prove for yourself is that the Milky Way is a spiral galaxy. You can actually perform the experiments that were performed by astronomers decades ago to prove that the Milky Way is a spiral galaxy. To me, that's fascinating to see the actual evidence yourself of what's going on there. We do this drift field. I mentioned the drift field over time. We can get a very grand picture of the Milky Way at hydrogen line. And we get multiple instances of the hydrogen line. And this is what talks to the spiral arms of the galaxy. We see multiple instances of the hydrogen line that are Doppler shifted. So we're seeing a large intensity, and then a smaller intensity at a different frequency, and a smaller intensity at a different frequency, which leads us to the fact that we're looking at 3 different spiral arms of our galaxy. So that can be demonstrated. One of the things that comes out of that, though, I mentioned there's a conundrum. The conundrum is this. We can't prove it, but we can demonstrate that there's something out there that we call dark matter. If we calculate the radial velocity at various points of the Milky Way galaxy, okay, we calculate it, and then we go and measure it, they disagree. And they disagree by quite a bit. This led folks to wonder what would cause such a great change in velocity. Well, one thing that will cause a great change in velocity is extra mass. So they talk about this halo of dark matter that surrounds the Milky Way would account for this. Now, who knows if that's really what it is? It's one theory. But again, it's something that we can actually measure and see. We can calculate the angular velocity based on what we believe the total mass of the Milky Way is, based on our knowledge of the Milky Way. But when we actually measure it, it's a different number. And I'll show you an example of that in a minute. So we measure it, we calculate it, and they don't agree. So this is where they came up with this concept of dark matter. They can't account for that extra matter. Where is it? We can't see it. It must be dark matter. So Pictor is a great way to see this. Pictor, I mentioned this online radio telescope. Pictor is wonderful. This is a typical result you get from Pictor, and I'm going to focus on one chart out of this. But essentially what you do is you go to the site, the Pictor site, and you set a time that you want for your observation, and you set a duration, let's say 5 minutes of observation at a particular time, because you know the telescope's going to be pointed at a particular location at that time. Let's say I want to look at Cygnus. So I figure out, when is Cygnus going to be over the telescope in Italy? And that's pretty easy to do with star charts and stuff. You can figure that out. I know when it's going to be over their telescope, and so I can set up a session. And what it does is it records the data. It'll process the data and email it to me. And this is what I get, is a chart that looks like this. Now, if I break down the charts, this is the one I really want to look at. This shows, I was talking about the 3 spiral arms. You can see them in this image. This is one that I recorded from Pictor. There are 3 distinct bumps here that are Doppler shifted. These are Doppler shifted hydrogen lines. Okay. So they're blue shifted to a higher frequency, which means it's a higher radial velocity, and it corresponds to 3 of the arms of the Milky Way galaxy. Each one is blue shifted a little bit farther, because the farther out it gets, the faster it's moving, which is nuts. But anyway, but think of points on a disk. What's happening there? So if we take data from all different directions, we can actually build a 3D model of the Milky Way galaxy. This is looking in one singular specific direction. But if I can start collecting lots of data and looking at all kinds of different directions and different elevations, what do I get? I get something that's going to kind of look like this. And this is an example. So that the chart I just showed you is looking towards Cygnus. So this is seeing the brightest part is the Cygnus arm of the spiral galaxy of the Milky Way. The next one is this guy, which is the Perseus arm of the Milky Way. And the third one is this one, the outer arm. This is the direction I'm looking. So you can imagine if I start plotting these individual measurements I make in 3 dimensions, this is a 2-dimensional image, but even if I just do it in 2 dimensions, I can generate an image like this in my backyard. But I don't even have to go into my backyard. I can go to the Pictor telescope and do this over time and get this. But here's where the problem lies. When we plot all these data out, and this happens to be, this is not the Milky Way. This is M33, which is another galaxy. When we plot it out, we do observations with starlight. Here, this is the starlight observations. This is observation from the hydrogen line. Down here is distance from the center of the galaxy in light years. So as we get farther out from the center of the galaxy, our velocity is increasing, which means that we're getting blue shifted farther. Now, when we look at the visible disk of M33 and estimate what the mass of the disk is based on our observations, this is what we should see. This is the expected curve. But that's not what it's doing. So this is something that's a direct observation. Now, this would be kind of hard for amateurs to do, but this is something that the radio astronomers look at intently, and are things like this. This is the whole thing about this dark matter theory, that there's a halo of dark matter, would account for the fact that it's higher radial velocity the farther out you go. So nobody's been able to prove it, but we can show it for the Milky Way. We amateurs can do this. We can either build our own telescope or we can use the online telescope. Obviously, the online telescope is the easiest way to do this. It just takes some time and a little effort, but you can actually demonstrate this, which is kind of cool. You're just observing hydrogen lines. So that is the modern conundrum that's come out of radio astronomy, believe it or not. It's pretty crazy stuff and cannot be explained. You'll see this is a very common topic today. So, not the expected results. So we've covered a lot of material here. What do you want to do next? What are we going to do? What I suggest, if you're really interested in this stuff, you really want to get involved in it, I encourage people to visit observatories. There's lots of observatories around that you can visit locally. Now, if you happen to be out here on the West Coast, and especially in the Los Angeles area, we've got the Owens Valley Radio Observatory, which is operated by Caltech. And I said, that's just 100 miles north of where we live here. Caltech runs that one, and they do offer visits. They host visits. Another place that you might visit is the VLA, the Very Large Array in Socorro. That's National Radio Astronomy Observatory. So nrao.edu, you can get information on that. They have a visitor center. You can go and check that out. So if you're somewhere in Midwest area, that would be a place to go. If you happen to be on the East Coast, I'd send you to Green Bank. I think Green Bank would be awesome. I'd love to visit Green Bank. That's the Green Bank telescope we were talking about earlier. And they have regular tours of that facility. If you're on Facebook, look them up on Facebook. They've got an amazing Facebook page and post a lot of material up there all the time. So that one's good. I've mentioned Pictor. Here's their website, pictortelescope.com, and I'll have a more on this later, another page of this. In fact, it'll be in the I'm going to send Dan a copy of the charts, and this will be in all the all the URLs will be in the charts because there's more coming. Radio Jove, this is their URL, their link. This is the Radio Jove project I talked about. In addition, you can check out things like SARA, Society of Amateur Radio Astronomers. And their website is radio-astronomy.org. That's a good one. One of the things that I love, this is one I discovered years and years and years and years ago. It was something called Bambi, and I got the biggest kick out of that. Bob and Mike's big investment. So these two guys built a hydrogen line telescope, and they're doing a lot of the same stuff that I'm just talking about here. But in those days, it probably took a lot of effort and a lot of money to make it work. But they were doing this hydrogen line, and some of their results are posted online. And it's Bambi.net. And I always get a kick out of that. I haven't looked at that for years. I hope it's still up and online, but I always got a kick out of that name, Bambi, Bob and Mike's big investment. So amateur radio telescope, there you go. Now, if you really want to get into this stuff, there's lots of suppliers of parts. This is one, radiotospace.com. They sell complete systems, LNAs, feeds, receivers, and down converters, all that hardware that you need. All that stuff is available. radioastronomysupplies.com is another one. Complete systems and components. They have all of this. The next one, I love these guys, and God bless them. They're in Ukraine. vhfdesign.com. Those guys are still producing parts. They've changed a little bit since the war broke out over there, but in the last year, these guys are still out there. They're still producing product, and it's still available. And they have got some superb products available for radio astronomy, especially their low noise amplifiers. They're relatively inexpensive. You can even find their stuff on eBay, as a matter of fact. But these are very good, low cost, low noise amplifiers. And I mentioned eBay. Don't forget about eBay. There's lots of stuff on eBay. LNAs, SDRs, little RTL dongles that you need, down converters, all this stuff that you need to build a telescope. No electric. I don't know how you pronounce that. I've got some of their hardware. They actually have some interesting stuff for doing a hydrogen line receiver that's actually geared towards doing that. This stuff is available on Amazon. And so they've got a 21 centimeter LNA, 21 centimeters being hydrogen line, as well as a SAW filter to go with that. That's a useful item to have. That's an interesting device, SAW filter, surface acoustic wave filter. So it's filtering RF energy, but it's using an acoustic wave, which is kind of cool. SAW filters and SDRs, they've got all of this stuff available online or on eBay, on Amazon. That stuff shows up there. And don't forget Amazon. Amazon's got all kinds of stuff. If you go start looking for LNAs for 21 centimeters, the SDRs and filters, this stuff will pop up all the time on there. So there's lots of sources. And it's interesting. I wish this stuff had been available when I was much younger, because I would have been playing with this stuff decades ago. I was always interested. I've been interested in this stuff since I was a little kid, but never had the resources to be able to do anything with it. Now I've got the resources, so it's easy now. But especially with these kinds of resources, it makes it trivial. It's an easy project. So there you go. That's the show, and I'm going to return this station to our normal programming.
Okay, Barry, what are we doing there in chat?
We're good in chat. A couple of the people mentioned the radio quiet zones around some of the observatories.
Oh, that's true. Yeah, the Green Bank especially has what's called the radio. It's the National Radio Quiet Zone, and you cannot transmit anything, even a cell phone. You can't use anything in there. So that's absolutely, yeah. Dave visited VLA. That is really cool. That's a great place to go to. Dan, you're talking about the James Webb Telescope. Yeah, you're right. I've been reading some of these discussions about the Big Bang. It's kind of interesting. One of the things that fascinates me is that what we can tell, what we measure, is the universe is expanding at an increasing rate, so it's accelerating. What does that mean? Now, what would cause the universe to accelerate? You know, you would think there would be an initial acceleration with the Big Bang, and then over time, it's going to gradually slow down, and then you're going to get the big squish. Everything's going to collapse back down on itself. But the evidence is contrary to that. So, who knows? I don't know. You know, I don't know the answer, but yeah, if there really wasn't a Big Bang, what would account for the background noise that's been assigned to the resonance of the Big Bang? Yeah, it's going to be interesting. The future is going to hold some really interesting stuff. Hey, Mike. Hi, my friend. Mike's up on the screen there. Howdy. Dark matter. Yeah, that's it. Oh, you live next. So John lives next to the VLBA antenna in the Virgin Islands. That's cool. I've toured the one up at OVRO. If you ever get a chance to tour it, it's really an interesting system to go see. Yeah, resolving power at JWST. I agree. That's an unbelievable instrument, and the results that they're getting from that are just Let's see. Are other countries involved? And if so, do they share? Yeah, there's a lot of collaboration that goes on internationally. Absolutely. If you look at a number of observatories, are collaborations of multiple countries, universities, organizations, and many of them, make their instruments available to, you think about something like OVRO. It's owned by Caltech, but I would tell you that there are probably researchers there that are from other universities, possibly in other countries. So yeah, there's a lot of that would go on. Yep. Dan, I agree with you that these are amazing. Let's see, what have we got here? Yeah, James Webb. Yep. Oh, science denial, huh? Okay. An EMP, what would that make it look like? That would disrupt things. It would probably destroy the receiver. But yeah, don't be afraid of science. Yeah, that's right. Excellent. Wow. Oh, you got to, okay, so Dave has a DirecTV dish. You got to build yourself a radiometer, or if nothing else, use it for a 10 gig transceiver radio and a sat finder. There you go. You got everything you need. You got it. Go check out Peter Wong's website. Very good, Dan. Yeah, always wondered. Yeah, I always wondered that too until I finally understood this, and it's like, wow, that's a pretty amazing thing that you can deduce from just making observations like that. Okay. Dan Sohn's gone. He had to check out. Okay. Checking into the nets. Yeah, Dan, you've been an optic. Me too. We have the Inyokern Observatory here. We have a permanent observatory, optical observatory here at the Faraday Fields, and we've got a couple of telescopes. One that's a permanent telescope is the LX200, 12-inch LX200 that we play with, and a couple of portable ones. So yeah, I've been doing this since I was probably about 10 years old. So I've been doing this since I was a kid. Peach Mountain. Yeah, definitely something You got to check out if they'll host visitors. Yeah, Green Bank is the National Radio Quiet Zone. Yes, indeed. I would expect that to be in Peach as well. Yeah. Now you have another hobby. Tell me about it. Well, see, you don't have to spend any money. That's the beauty of this. Pictor telescope, free to use. You can do your observations, which is really neat. Oh no, they're out of business. I did not know that. So they were still around the last time I did this presentation, which wasn't long ago. So that's a recent event. I'm sorry to hear that. Sorry to hear that. Yeah, that was a great source of hardware. Well, that's the chat. Anybody have any questions they'd like to ask or any comments? I appreciate the comments on there too. Thank you.
I don't see any hands up, and I think we'll cover the chat. Great presentation. And I'm getting some ideas for another presentation that you may or may not like.
Uh-oh. Well, try me.
I think we ought to follow up with the presentation sometime with just a one-night setup, showing people the simplest, cheapest way to get them going, get them going. To use the computer.
Actually show some of the results. Instead of links to websites, just show the hardware and show how you put it
and we'll set it up.
That's pretty simple.
You got yourself a thing going.
Yeah, it's actually pretty simple to set the. I've actually got a what is that? A 3 meter? I've actually got a bunch of dishes sitting out in the back here. One of which is raring to go that I'm going to use for hydrogen line is a 3 meter dish. But the one I really want to use is a 7 meter dish. But I don't have that up in the air yet. But that's a real simple thing. We've done that with portable dishes here, basically with an EME setup for 1296. If you do EME on 1296, you're readily easy to get on hydrogen line observations. You're basically using the same hardware. So if you're doing any kind of EME on 1296, you're set. It's real easy to do that. And that's what we were doing, is we were using a small EME dish to do hydrogen line observations. But Pictor's made it so easy. It's like, oh, I love that. And you know, what a cool idea to make it freely available to anybody to use it on the web. You know, that's a wonderful thing.
Mike,
I really admire that.
Did you have something you wanted to say, Mike?
No, except thanks, Dennis.
Oh, sure, Mike. Good to see you.
That was very interesting. I didn't know a gnat about about radio astronomy. I don't think I understood it all, but I think that you recorded this, right? I'd sure like to get it, because there's some sources in there that I couldn't copy down in time.
We'll have Dan posts a recording as well as the hard copy of the presentation, and I'll put a resource page up with all the links, so that'll all be available in a few days.
All right,
I can send you the information. Since I sent this to you, I can send you the information for that as well. Get you to subscribe to RATPAC, then you can join us all the time.
What?
You can join us all the time here. We do this twice a week.
Oh, I didn't know that. I will. Okay, good. Am I on how do I get on the mailing list?
It should be on the email I sent you. It should all be there. Mike is one of my, if you see his background there, his background's a lot like my background. We're both into collecting vintage radio gear.
Oh, okay.
We talk on vintage gear with each other all the time, which is a lot of fun. He's got quite a nice collection there.
Is it the same meeting code all the time?
Uh-huh.
Okay.
Yeah, it's the same Zoom session, same session and the password.
Okay, thanks, Dennis. I got to run, but bye, everybody. And a wonderful talk, Dennis.
Thanks, Mike. Appreciate that. We'll talk to you later for sure.
Okay, for sure.
Be good. Well, any other comments or questions? Any questions that I can try and answer?
There's a good question in the chat.
How do you contact me? Easy. My call sign at arrl.net. So W6DQ@arrl.net.
Actually, there's a question on how big a problem are the new cellular bands interfering with radio astronomy?
Probably not, because they're, again, the hydrogen line, that water hole is protected spectrum. ITU protects that. So you won't find any cellular transmissions in that chunk of spectrum, thankfully. Although it can interfere. That's why Green Bank has got the radio free zone there, because they do get interference from these are sensitive receivers. And if there's any spurs from a radio, they're going to get detected. I will confess that a couple of us get to work with the guys up at OVRO all the time. I've done a lot of work with them over the, if you were here to see the talk I did on EME on 40 meters, that was done with one of their telescopes. We used their 40-meter dish to do moon bounce. And so we've built a relationship with the observatory. When they built the LWA, the long wave array, they have no experience with HF radio. They don't know what they're looking at in terms of interference. And so they called upon us, a couple of us that are involved with with the programs up there, to come and help them sort out some issues with the telescope, which to me was astounding, that these guys asked me and another friend of mine to come up and look at the telescope and help them sort out some problems with it. And they turned out to be things like common mode noise in the way they assembled it. It was the LWA, 128 antennas. And you want to talk about ground loops. There were lots and lots of ground loops, and it was messing up the data. But nowadays, they're getting interference, and they're trying to figure out what the interference is. They don't recognize it. They don't know what it is. They're in a pretty quiet area. They're a ways away from any. There are no major cities. There's a couple of small towns close by, and the city of Bishop, which is a larger town. They do get some interference from there. And you can actually see it you can actually see where the interference is coming from and pinpoint it. But they were getting interference from, if you're familiar with what an ionosonde is. Ionosondes are, it's an ionospheric radar where they basically have an antenna pointed straight up in the air that's bouncing HF signals off the ionosphere, and they're measuring the time delay. And with that time delay, they can measure the height of the ionosphere as well as the charge density. And what they do is, you'll see, if you have an SDR, you'll see these things all the time. It's just a carrier that sweeps right across your display. And so you'll just see this slanted line cutting across the display on your waterfall. They had no idea what it was. And I wrote back and I said, Mark, I think that's an ionosonde. And he goes, by golly, I never thought of that. That's exactly what it is. Yep. The frequency range and everything was right on. So they do get interference, and they have to be sensitive to that stuff. Once you've identified it, you could deal with it. If you identify a source of interference, you can deal with it. But I'll tell you, something like GBT or VLBA, those are immensely huge antennas, if you synthetic antennas. So yeah, the slightest amount of interference really messes with the data. So yep. But yeah, I don't know of any interference from any primary interference from cell phones, because the ITU protects it. So that's what to be aware of. And of course, you start getting up into the stuff where they're doing research these days in millimeter and submillimeter wave astronomy. There's very little interference with anything up there. And yes, James, I absolutely 100% agree with that. There's been many proposals over many years to build a radio telescope on the backside of the moon, facing away from the Earth, so it's not plagued with noise. And I hope to see that sometime in my lifetime. That would be fabulous, but I don't know if I'll live long enough. That would be an incredible instrument to see.
Yeah, as long as we go into the moon anyway, we might as well pack along.
Yeah, why not?
Get up and gold bag to put that together.
Yeah. Well, you could do well, 5G is not quite millimeter wave, I don't believe. Not yet anyway. It's microwave. Frequencies that they're using, I don't consider those millimeter wave, but maybe, yeah. Oh, really? Okay. I believe you. I just never thought about that as being 26 gigs. So I don't think of 26 gigs as being millimeter wave. That's still a pretty big wavelength. Millimeter wave, I mean, 26 gigs, that's WR42. That's big enough to see the stuff. Millimeter waves, you can barely see the stuff. Up to 71 gigs. Okay, that I was not aware of. Okay. I was not aware that they're operating up at 71 gigs. Wow, that's some good information. I'll look into that. Check it out. Thanks. Aha. All right.
All right, well, we've gone over, but that's okay. It's a great presentation, worth it.
Thanks, Dan.
Any more comments? Any more? Wait a minute, Dan's in here someplace and he hasn't said a word. This is.
Oh, Dan left.
Oh, he did.
Yeah, he didn't make any. The only comment he made a comment about having to leave to go to one of the local nets over in the valley. So yeah.
Yeah, we have some people on here, regulars, and they have a MO, if you will.
Yeah, gotta love him. Dan's great.
He is. I enjoy him a lot.
He's my section emergency coordinator. I'm his assistant section emergency coordinator. So yeah, we're in contact a lot these days.
Yeah, he missed his beating life. He hasn't been a ham radio operator very long, actually, and it's just his nature.
He's grabbed the bull by the horns, that's for sure.
Yeah, that's right.
Mm-hmm.
All righty, I'm going to make another call out here. Is there any comments, any ideas, suggestions? I still like my suggestion earlier. We'll talk about it in planning. I don't see anybody, so I'm going to pull the plug here, and we'll see who shows up tomorrow night, Thursday, same time, same channel. Before
you kill it, Dan, Brian, yeah, please email me. And one of our members of the of our steering committee for RATPAC is also a member of TAC. But I'm not. She's not. Michelle's on. What is that? Artificial intelligence, and I can't think of what the other. It's a dual role. I can't think of what it is. But yeah, and I put you in touch with her as well because she's very interested in this stuff. So,
yeah, sounds good. I'll email you.
Okay, I appreciate that.
Yeah, because this is one thing, as we're moving up to 6G, we're talking about going into terahertz, and
yeah.
So.
Yikes. Yeah, it's going to create a whole new wave of problems. That's for sure. Yeah. Yep.
Well, that's how we go forward, is problems to solve.
Yep, that's right. All right, everybody. Well, thank you very much for joining us, and I thoroughly enjoyed doing this, and I hope everyone got something out of it, and maybe you'll find yourself a new hobby or just something to dabble in. It's exciting and it's interesting and not something that everybody does. So it's kind of a cool thing.